Okay.
I'm going to work example 15.11 for you. We have an oblique impact, and we know that because the velocity vectors are not along the line of impact. They are some angle theta relative to that line. Velocity of B is coming in at a 45-degree angle, and velocity of A is coming from the bottom left with a 30-degree angle. But we kind of need to make sense of what those angles are so that we can hold on to the sign properly. In the book, they don't use 225 degrees as the actual angle for the velocity of B. They just throw a negative sign on it and use 45 degrees. If you use the correct angle measurement, the sign will come out for you. So when they collide, they're going to have some coefficient of restitution as 0.75, and they're going to move off with new x and y components of momentum for each. From that, we can figure out what the velocities are. So we want to find the velocity of A after the collision in the x and y direction, and the velocity of B after the collision in the x and y direction. Just a note, if you see a coefficient of restitution, we cannot conserve energy. Only purely elastic collisions can we conserve energy. Okay, so I'm going to take my initial velocities and calculate them out and break them into some numbers that we can plug in. So the velocity of A in the x direction, initially in the x direction is going to be the 3 meters per second times A is going at a 30-degree angle relative to the x-axis. That's the axis we measure from. So let's use the cosine of 30. And so that gives me 3 root 3 over 2 meters per second. If I want to look at the velocity of A initially in the y direction, we'll do the same thing with the sine of 30. And that gives me 1.5 meters per second. For the velocity of B, I'm going to use 225 degrees as measured from the positive x-axis. So the velocity of B initially in the x will be the 1 meter per second times the cosine of 225, and that gives us a negative root 2 over 2. And the same thing for the y direction. Sorry, not the cosine, the sine of 225. But they have the same value as negative root 2 over 2. Alright, so we have our initial velocities broken down into something that we can now use the conservation of momentum with. So let's do it. Let's conserve momentum in the x direction. And why the x direction? So if we look at the problem, we excuse me, have mass A times the velocity of A initial in the x direction plus mass B. We're looking at the whole system times the velocity of B initial in the x direction, and that's going to give mass A some new velocity in the x direction and mass B some new velocity in the x direction. Okay, from this we have enough information to reduce it down to our first equation. We'll call it number 1. Plug in everything and rearrange, and you can get that the velocity of A final in the x direction plus 2 times the velocity of B final in the x direction is equal to 1.184 meters per second. Okay, let's hold on to that equation number 1 and let's apply our coefficient of restitution. So we have E given to us as 0.75 in this problem. We use the formula velocity of B final minus the velocity of A final over, we have the velocity of A initial as 3 root 3 over 2 and the velocity of B initial as negative root 2 over 2. Alright, so if you simplify this one, we can also get another equation. So we have 2 unknowns right there, we need 2 equations. So I can get the velocity of B final in the x direction equal to a 482 plus the velocity of A final in the x direction, and we'll call that equation number 2. If I do 2 into 1 to eliminate a variable, we can get the velocity of A final in the x direction to be negative 1.26 meters per second, and the velocity of B final in the x direction to be 1.22 meters per second. Alright, so we have our x direction taken care of. What about our y direction? Since the collision is said to have only occurred in the plane of contact, that's where the restitution occurred. So when these things hit, one was coming in from this direction, one was coming in from this direction. When they squished, they only squished along this plane, and that's the plane the coefficient of restitution acted on, and we had to use that to get our second equation. What we know is in the y direction that velocities are conserved and we have a total conservation of momentum. So what this says is that the velocity of A in the y direction, initially in the y direction is going to be equal to the velocity of A final in the y direction, and the velocity of B initial in the y direction is going to equal the velocity of B final in the y direction. And we had those values calculated as 1.5 meters per second and negative root 2 over 2 meters per second. Alright, if we wanted to put that back into vector form, we could. The velocity of A final is equal to some negative 1.26 I plus 1.5 J meters per second, and the velocity of B final is a positive 1.22 I minus 0.707 J. And that's also in meters per second. Just a real quick example of how this deformation stuff works. If I had a bouncy ball that was about to hit the ground, but it was traveling in this direction, then we're going to have some sort of trajectory, right? Right before it hits the ground, or right when it hits the ground, it's going to deform in that direction. So only squish is going to occur in the y direction in this case, and some coefficient of restitution is going to not allow us to get to the same height we started at. So if it bounced again, it's going to squish some more and then not even bounce up. So we're going to lose some more height. Alright, let me know if you have any questions.